Quantum chemistry. I chose quantum chemistry because when I hear the word quantum, I think of future technology, and to me that's interesting. What is quantum chemistry? Simply put, quantum chemistry is the application of quantum mechanics to chemical systems. But what are quantum mechanics? Quantum mechanics is the laws of physics for very small and very light objects like atoms and molecules. Culture. Quantum theory is largely known for being unknown, known for not making sense and seeming untouchable. Quantum theory is often attached to the mysteriousness of the universe, which alone has been more influential to pop culture than any other scientific mystery. The unintuitive, almost alien-like nature of quantum mechanics sets it apart from classical mechanics, which kids are taught, giving quantum mechanics an air of radicalism. Geography. Atom colliders, or particle accelerators, are mainly used to study particle physics, i.e., quantum mechanics. There are 30,000 in operation over the world, many of them underground, and as you can see, they can get quite large. Geography plays a vital role in where these are built, if the ground is made of the right materials, accessible by many workers, and they have to try to find a place where it will minimally harm the environment. Problems in quantum chemistry. Environmental, ethical, and social problems. One major problem that can come from studying quantum physics through particle accelerators is that they emit ionizing radiation while they are operating and can produce radioactive waste, which is very harmful for humans and the environment. Another problem is when large particle accelerators are built underground, they can displace many animals who live there. Large particle accelerators built above ground can leave less space for people to live, making the construction of these buildings both an ethical and social dilemma. The building you see is the longest building in the world, and it was built for a particle accelerator. For reference, the two buildings on the left from left to right are the Empire State Building and the Burj Khalifa, which is the tallest building in the world. One ethical problem came when researchers at a particle accelerator used a ferret to clean accelerator parts, which gave the ferret radiation and eventually died on the early side for a ferret. Another potential problem with particle accelerators is that they can create black holes. Now currently we can only create miniature black holes which pose no threat to us or anything, but if we keep building bigger and bigger colliders, then black holes will become a problem. Another problem with quantum chemistry is that the nanotechnology in everyday technology like smartphones and computers uses quantum chemistry as its core, and the materials used for these parts often harm the environment to acquire and sometimes can be unethically obtained. This is Felicia, the ferret that they used to clean the accelerator part. History. In the early 1890s, the German Bureau of Standards asked Max Planck how to improve the efficiency of light bulbs. The first thing he tried to define was how much light was emitted. He knew that light consisted of different colored and of different frequency electromagnetic waves, but he needed the output from the light bulb to be mostly visible light. He tried to define the output using the physics standards of light at the time, but his predictions using these standards disagreed with his experiments. In what he later called an act of despair, he disregarded the current knowledge of how light and heat interact and started from scratch. The data he got from these new experiments told him that light waves carry energy only in packets, with high-frequency light consisting of high-energy packets and low with low. The idea that light traveled in packets or quanta was a crazy idea at the time until Einstein, a very good friend of Planck, related the idea to sharing. If you tried to share an apple evenly among two people, each person would get half an apple. If you tried sharing that same apple amongst infinite people, each person would get an infinitely small piece and thus would not be very happy. Now we can't have infinite people in a room, but there could be infinite light waves because of the variation in the size of the waves. Since we know that the waves could draw more and more energy as they become of higher frequency, then if there was a room with infinite light waves, the waves would infinitely take the energy out of the room, instantly freezing anything in it, even if the sun was inside of that room. Thankfully, this isn't how the universe works, because as Planck guessed, the tiny high-frequency packets can only carry away energy in huge amounts. They are like a person who asks for 20 apples, no less and no more, and because of their inflexibility, they lose the battle, and light is carried out in lower energy, lower frequency packets because they are willing to share. The average energy of these packets is actually synonymous with temperature. A higher temperature just means a higher average of energy output, and thus by Planck's rule, a higher frequency of light emitted. This is why an object gets hotter if it glows and farther along the scale of light frequency. Think of the varying colors of fire. Planck's quantum theory of light helped him determine the most efficient heat for bulbs to be at, which was 3,200 Kelvin, and is the origin of quantum mechanics. The chemistry. To have even the smallest understanding of quantum chemistry, you have to understand the basics of Schrödinger's equation. In short, the equation tells us everything we need to know about a quantum system. It's basically the F equals ma, force equals mass times acceleration, of the quantum realm. If you throw a ball into a box, you can determine where it is in the box using F equals ma, but when you apply the same scenario to the quantum level, F equals ma becomes insufficient. A major principle of quantum mechanics is Heisenberg's uncertainty principle, which says that you can't know the exact location and the momentum of a quantum object, which makes F equals ma completely useless. But there are a few things we can know, like energy and the wave functions, which are all inside the Schrödinger's equation. To further explain the equation, I would have to go in depth on many symbols and even deeper equations behind them, which would just take too long. Another core building block for quantum chemistry is how electrons work. Because electrons are in constant movement, they should be losing energy and thus slowing down. We now know this to be wrong, but back then no one understood it until Niels Bohr, a Danish physicist, explained it. Electrons orbit the atom at specific energy levels and exact orbits. The energy level in the rings lowers the closer as you are to the atom, and thus slows the electron. The reason the electron never slows to a stop, is because an electron can do one of these three things at all times. It can either jump to a more powerful level, gaining quantum energy, aka a photon in the process, or it can do the opposite and lose a photon as it goes to a lower energy level, or it can stay at the same energy level. The reason that the lowest energy level isn't the electron falling onto and colliding with the proton is because if this happened, then the location and momentum of the electron could be known better than is allowed by the Heisenberg uncertainty principle. So that was Schrödinger's equation and the stability of an atom, which are in almost everything that has to do with quantum chemistry. These are my sources, and thanks for watching.